The hardest problems aren't a bug. They're a feature of geometry.
Welcome to SpaceTime Cafe. I'm your host, and today we're diving into the fascinating theory of obstruction. Enjoy the show.
Welcome back to the deep dive, everyone. We're recording here in our Austin studio. And if you happen to be watching the visuals for this one, you'll see we've been playing around a bit behind the scenes. Our new video editor, they've pulled out all the stops, some absolutely stunning visual aids that I think are really going to help make some of these pretty abstract concepts feel much more tangible today.
Yeah, they've really managed to turn what could be quite dense ideas into something visually captivating. It sets the perfect mood, I think. Last time we took this fascinating journey, didn't we, into how our own sense of agency, our ability to choose, is tied to the thermodynamics of irreversible decisions. We talked about the basic physics of choice and how every commitment we make leaves this kind of indelible mark. Today, we're pivoting in just a little bit, but we're definitely staying in that realm of the profound. We're going to tackle a question that I'm guessing has puzzled pretty much every single one of you at some point. Why do some problems feel absolutely impossible, like you're just hitting a brick wall?
While others, even really complex ones, sometimes just seem almost trivial. You felt it, right? That one stubborn puzzle you can't crack, maybe a coding challenge that just won't give, or trying to organize your closet sometimes. You hit this invisible barrier. And it feels like there's something fundamentally different about these problems. A hidden obstacle, that simple effort, or even just brute force, it just can't overcome it. It's not about just being clever enough, is it? It's like the problem itself is actively resisting a simple solution. So what is that wall? What makes these specific problems so uniquely difficult?
Well, what's really fascinating here, as you just said, is that it often isn't a different kind of wall. It really does seem to be the same hidden obstacle cropping up again and again across fields that look totally unrelated on the surface. We're talking about something mathematicians call a topological twist, and the technical name for it is a Gerbe obstruction. Now, this isn't just some vague philosophical idea or rhetorical explosion. No, it's a tangible, measurable mathematical feature. It's a property that's inherent to the structure of the problem itself, like a deep geometric property. And what's truly astonishing is how universal it seems to be. This same twist appears whether you're wrestling with deep questions in physics, or the hardest computer science problems like PVSNP, or even designing unbreakable encryption. It seems to be a fundamental property of difficulty itself.
Okay, well, that sounds less like the wall and more like a cosmic secret handshake for difficult things. A hidden fundamental law.
Yeah.
What are we going to uncover from this deep dive?
Well, we're going to take you on a journey through these ideas. First, you're going to learn what a gerbe actually is. We'll explain it simply using a pretty intuitive analogy. Then we'll show you how its Dix-Merer-Duati class, or DD class, serves as a precise mathematical measure of computational hardness. Think of it like a difficulty score for any given problem, or a twist number that tells you exactly how knotted up it is.
Exactly, a fingerprint of its complexity.
Right.
Then we'll reveal this profound connection between irreversible choice, those simple decisions you make that you just can't take back, and how that action literally embeds this twist into any search landscape, making problems intrinsically difficult. Finally, we'll explore how this abstract twist shows up in very concrete, real-world areas, stuff like the infamous P versus NP problem in computer science, all the way to the cutting edge of modern cryptography. So yeah, these terms might sound a bit daunting right now, Gerbe, DD class, but trust us. By the end of this deep dive, they should be crystal clear, and you'll likely have a completely new way of thinking about why some problems are just so darn hard.
Indeed. I think you'll find the mathematical elegance behind it and how far-reaching the implications are quite beautiful once you see the pattern.
Okay, let's start with that intuitive analogy. Imagine trying to cover a perfectly smooth globe, like a beach ball, with flat pieces of paper to make a map. If you just take two pieces, maybe one for Europe and one for Asia, you can probably get them to overlap pretty nicely where they meet, right? Locally, everything seems to fit okay. The seams look tidy, the countries line up at the borders, you can kind of smooth it down and make it work. But here's where it gets interesting. What happens when you try to glue three map pieces together at once? Say you have a patch for Europe, one for Asia, and one for North America, and they all theoretically meet at a single point, like near the North Pole. You can try to smooth it, stretch it, pull it. But you often find there's this microscopic warp, a subtle mismatch that makes the edges refuse to line up perfectly. There's like a tiny gap or maybe a little wrinkle you just can't get rid of without tearing the paper or creasing it fundamentally. That frustrating feeling, that inability to make the third piece join perfectly, that subtle twist, that's your intuitive starting point for understanding this Gerbe thing.
That's a perfect intuition, that precise frustration you described, that irreducible mismatch when you try to join three things. That's exactly how mathematicians started thinking about these structures. Initially, they developed concepts called fiber bundles. Those deal with how you attach local data, like little arrows representing wind direction or maybe some property to every point on a space. And crucially, how you transitions between two overlapping patches or charts. The classic example is a Mobius strip, right? Locally, any piece looks flat, like a normal strip of paper. But globally, when you connect the two ends with a twist, it's fundamentally different. You can't flatten it without cutting it. That's a fiber bundle phenomenon. But when you move to the more complex scenario, like your three map pieces trying to overlap at the North Pole, where you're trying to join three local views simultaneously and consistently, well, that's where Gerbes come in. So a Gerbe isn't just about things not fitting nicely between two pieces. It's about a kind of higher order failure to compose. It happens when you try to join local solutions or local symmetries, or like in your analogy, glue three or more local pieces together consistently. There's a breakdown in the consistency rules. To get slightly more technical, a Gerbe is a sophisticated mathematical structure that generalizes fiber bundles. Think of it like this. A fiber bundle might attach a simple piece of information, like a number or an arrow, to each point. A Gerbe goes a step further. It attaches systems of rules or local universes of possibility, not just to points, but to the overlaps between patches. The critical mathematical condition is that when you try to follow a path through three overlapping regions, let's call them alpha, beta, and gamma. So you go from alpha to beta using one rule, then beta to gamma using another rule, and then gamma back to alpha using a third rule. You don't quite end up exactly where you started in terms of the internal structure or rule. There's a non-composition, a subtle slip that reveals this inherent twist. It means the transition functions, the rules for moving between patches, they don't multiply together nicely when you try to chain three of them in a loop like that. It's mathematically represented as U alpha beta gamma alpha 2 Janda. That product isn't the identity. There's something left over.
Okay, they don't line up perfectly. So what does this mean for us, the listeners? Why should we care about these mathematical objects where things don't quite compose perfectly on these triple overlaps? How does this abstract idea connect back to the real world problems we face? Figuring out the best delivery route, understanding physics, cracking codes. What's the practical impact of things that don't quite fit together smoothly?
That's exactly the key question. And it leads us directly to how we measure this twist, how we quantify it. Mathematicians use something called the Dixmuir duity class, or DD class. It's the precise mathematical quantity that measures this twist. You can think of it like a topological GPS coordinate or a twist number. It's a specific kind of mathematical object called a cohomology class. You can imagine it as a unique fingerprint that tells you about the irreducible lumpiness or twistedness of a space, something that can't just be smoothed away by changing your perspective slightly. In our case, the DD class tells you precisely how twisted a problem structure is in a way that's fundamental. If the DD class is 0, the Gerbe is called trivial. That implies a globally flat structure, like your smooth bowl analogy for easy problems. For problems, it often means they're relatively easy to solve, or at least they don't have this specific kind of topological obstruction. But as DD class is non-zero, that means the space is fundamentally twisted. It signals inherent difficulty and obstruction that any solution method has to somehow navigate or overcome. So this DD class is the key number. It tells you if a Gerbe is twisted, and essentially by how much. It provides a concrete, measurable invariant for a problem's intrinsic hardness.
And this is where it gets really wild, right? Connecting this abstract mathematical measurement to something, well, almost universal. You mentioned before an astonishing discovery, that this very twist for many foundational problems can be represented by a single universal mathematical signature. What is this cosmic watermark you called it?
Yes, it's quite remarkable. It's called the Wess-Zumana-Witten 3 form, often just abbreviated as WZW. Its universality is truly profound. This specific mathematical originally popped up in quantum physics, specifically in studies of quantum anomalies, and also in string theory. It also appears in pure topology, measuring fundamental properties of spaces, like how certain loops can be filled in. And now it emerges here as the definitive measure of a problem's twist in this Gerbe context. The fact that the same mathematical form appears in quantum field theory, topology, and now in the study of computational complexity, well, it strongly suggests a deep underlying universal structure to difficulty itself. It's like the universe has a preferred way of encoding hardness or obstruction. Now, this WZW form is mathematically linked to something called the restricted unitary group, denoted de Mathurin called. It's a vast, infinite dimensional group that carries the universal Gerbe. Specific problems, whether in computer science, physics, or inherit this obstruction via pullback. Think of it like projecting a complex shape onto a flat surface. The shadow inherits some properties of the original shape. Here, the problem inherits its twist from this universal gerbe carried by one Earth. It's like a cosmic watermark stamped onto its very structure, dictating its fundamental difficulty.
Wow. So this isn't just about complex math then. You're saying about a fundamental property of how hard is actually baked into the universe itself, whether we're talking about a particle interaction, a mathematical puzzle, or even the decisions we make every day. That's quite a statement.
It suggests that difficulty isn't arbitrary or just a matter of scale. It's a geometric and topological feature woven into the fabric of reality, consistently present in the deepest structures we observe.
Okay, let's talk more about those decisions we make. Can you really flesh out that divide between a fully reversible action and an irreversible one? Like, think about ideal quantum evolution, the Schrödinger equation stuff. In theory, it's perfectly invertible, right? You can always run the film backward, mathematically speaking. Every step has a clear, unambiguous inverse. No information is truly lost. But then, what happens when you actually perform a measurement in a quantum system? That feels very different. That's an irreversible act, isn't it? You can't truly unmeasure something once you've observed it, right? The wave function collapses, as they say. Or you can't undecide a choice once its consequences have rippled outwards. The information seems locked in somehow. It's like breaking a glass. You can glue it back together, maybe, but it's never exactly the same. You can't unbreak it.
Precisely. That act of fixing a bit, whether it's a measurement, collapsing a quantum state, or making a definitive choice in a complex system, or assigning a specific value, true or false, to a variable in a computational problem, like fundamentally breaks that perfect reversibility. This seemingly simple, irreversible local operation turns out to be the surprising mechanism. It's what introduces this topological twist and, as a direct consequence, computational hardness into the system. It's the point where ambiguity collapses, where multiple possibilities narrow down to just one. And in doing so, it creates a very specific kind of structural rigidity, a non-trivial topology. This leads us to a precise mathematical result. We're calling it the Gerbalock theorem. What it states, essentially, is that any irreversible local choice forces a non-trivial two-Kant cycle, thereby embedding topological complexity into the system. Initially, you might imagine a system is in a globally ambiguous state, a superposition of choices where many possibilities exist at once. In this state, the gerbe representing its structure might be trivial or flat, easy to navigate. But then you perform an irreversible operation within the local region. You make a specific choice. You perform a measurement. This act introduces a discontinuity or a cut at the boundary of that local region where the choice was made. This profoundly modifies those transition functions, the rules that glue different patches of the system's possibility space together. As a result, the original co-cycle, which was trivial, gets deformed into a non-trivial one. And the consequence is significant, as the theorem states. The irreversible choice introduces a non-trivial Gerbe structure by deforming the original trivial co-cycle. If this new deformed co-cycle is non-zero, if it represents a genuine non-removable twist, then the previously smooth and reversible landscape of possibilities becomes rugged and topologically obstructed. It really is like a once flat, easy-to-navigate surface suddenly developing insurmountable hills and valleys. It becomes impossible to find a smooth, continuous path between certain points or states. This dramatically increases the topological complexity of the problem space, making it much harder to navigate or solve efficiently.
This is really fascinating. So making a choice you can't undo literally twists the underlying mathematical space of the problem itself. That's profound. Let's try to bring this down to earth, though. Can we use a toy example, something you can really visualize? Imagine you have 5 identical coins in a row. Each one is either heads, one, or tails in a row. A move is just flipping one coin. Easy peasy. But here's the twist. We define a single global value. Let's call it omega, based on some of the coins. Let's say omega is the parity, whether it's odd or even, of the sum of coins 0, 1, 3, and 4. So omega takes parity of M0 plus M1 plus omega 3 plus omega 4 is there. And here's the hidden rule, maybe the public encryption rule. You flip the coin at index 2 again, an extra time, if and only if that omega value equals 1. It's a rule that depends on a combination of other coins, not just the one you flipped. It's almost imperceptible unless you know to look for this specific global condition. It links local actions via a global property. Walk through an example.
Maybe you start with a secret message encoded as the first 3 coins, say 1, 0, 1, and the last 2 are just padding, 0, 0, 0. So pin on 100. Now you decide to perform a sequence of flips as part of your encryption. First you flip coin 0, then you flip coin 1, then you flip coin 2. Now, naively, if there were no hidden twist rule, you'd calculate the result based on those 3 flips. Simple reversal would get you back. Because the sequence involved flips on coins 0, 1, and 2, and specifically because coins 0 and 1 are part of that omega calculation. Let's see. If the parity of M0 plus M1 plus M3 plus M4 becomes 1 at the end of the sequence, then the twist gets activated. An extra invisible flip of coin 2 happens right at the very end, triggered by that hidden rule. The final state of the coins is not what you'd expect just from the 3 explicit flips you performed. It's subtly different, specifically on coin 2. Okay, now imagine you're the decryptor. Get this final twisted coin sequence.
You know, the intended flips were flip 0, then 1, then 2. If you just try to reverse those intended flips, flip 2 back, then 1 back, then 0 back, without knowing about the secret twist rule involving omega, you'll get the wrong answer. You'll be off by exactly 1 flip on coin 2 because you didn't count for that extra hidden flip that might have happened. It's a simple setup, but it just won't unwind correctly for you if you don't know the rule. You're navigating a space that's been subtly twisted, and you don't have the map, the key, to untwist it.
And that's precisely where the secret key comes into play in this analogy. The secret key isn't some complex number. It's simply the knowledge of the twist rule itself. It's knowing that an extra flip of coin 2 occurs under certain parity conditions involving coins 0, 1, 3, and 4. With this knowledge, you can untwist the ciphertext. Before you reverse the intended flips, you first check the parity condition, omega, based on the received state. If it's 1, you apply the anti-twist. You perform 1 extra flip on coin 2 to counteract the hidden flip. Then you reverse the intended flips, 2, 1, 0, and voila, the original message, the initial state on level 100, reappears perfectly. This 5-coin puzzle perfectly illustrates the core idea, how a single, seemingly simple, irreversible twist locks in hardness. It makes naive reversal ambiguous, impossible even. And it shows how knowing the anti-twist with secret key allows you to recover the original information. It's arguably the simplest possible problem where local actions have a non-trivial global interaction that breaks simple reversibility for anyone without the secret knowledge. It's a basic model showing how a secret can be embedded not just in the steps of a process, but in the very how those steps interact.
Okay, that's a clear example. A 5-coin puzzle shows how a twist creates a simple cipher, locks in information. Very elegant. But how does this idea scale up? How does it apply to real, truly unsolvable problems, the big ones like 3 SAT? That's a cornerstone problem in computer science, right?
Yeah.
It underpins the whole PV/SMP question. How does this abstract topological twist manifest itself in something as complex as Boolean logic, where you're dealing with hundreds or thousands of variables and trying to satisfy a huge list of logical constraints?
That's an excellent question, and it's where the power of this framework really becomes apparent. It does scale, and quite directly. For any given instance of can define a specific mathematical object. It's called a Dijkgraaf-Witten 3-coast cycle, and it's constructed based on the parity relationships between clauses that involve triples of variables. It captures how satisfying one clause might affect the possibilities for satisfying others involving shared variables, but in a subtle 3-way interaction. This specific 3-coast cycle is the mathematical object representing the 3 SAT gerb. Our analysis, based on prior work in related fields, rigorously shows that for typical hard instances of 3 SAT, this 3-coast cycle is non-trivial. It defines a non-trivial class in the cohomology of the problem's configuration space, specifically HG122. In simpler terms, this proves that the Gerbe obstruction is a real, non-vanishing topological invariant inherent in the structure of hard 3 SAT problems. It's fundamentally there. Now, the significance of it being non-vanishing is crucial. Think about a knot in a piece of string. If you can shake the string and the knot disappears, it was trivial vanishing. You could gauge it away. But if it's a real knot, like a figure-8 knot, no amount of shaping will make it disappear without cutting the string. It's non-vanishing. Similarly, in mathematics, a vanishing cocycle can often be gauged away by cleverly redefining your coordinates or basis functions. But this surviving, non-vanishing cocycle in 3 SAT means the twist is intrinsic. It's fundamental. You've effectively built a Mobius soul into the very structure of the problem. You cannot flatten it out globally without tearing the fundamental fabric of its solution space, without introducing deep contradictions or inconsistencies. So, the hardness in this view is baked in at the topological level. It's inherent to the very structure of the problem's landscape of possible solutions, not just a matter of having too many combinations to check.
Okay, so the problem's inherent twist makes it structured topologically rugged. How do we visualize that ruggedness? And how do we measure it in a way that connects to computation? You used that great analogy earlier of a solution landscape. Imagine you're blindfolded, walking around in a hilly area, trying to find the absolute lowest point, the deepest valley that's your optimal solution. An easy problem, you said, is like a smooth, simple bowl. No matter where you start, you just feel which way is downhill. You walk that way, and boom, you're guaranteed to find the bottom quickly and easily. It's a convex problem, basically. Describe the landscape for a hard problem, like 3SAT.
It's definitely not a simple bowl, is it? Yeah, like the Himalayas.
A rugged, confusing maze of countless hills and valleys, thousands of false valleys, little local dips that look like the bottom, but they're not the true global minimum. You could easily get stuck in one of those small dips thinking you found the solution, with no obvious path leading towards the real lowest point. There's no single, consistent downhill direction that works everywhere and guarantees you'll find the global optimum.
Exactly. And we can actually quantify this tangledness or ruggedness using a concept from topology called Farber's topological complexity, usually denoted TC. TC measures, roughly speaking, how many distinct continuous rules or motion planning algorithms you need to be able to navigate between any 2 points within that solution space X. A simple space like a bowl has TC1, one rule, go downhill, works everywhere. A more complex space needs more rules. Now, Farber and others proved a crucial link. A non-trivial Gerbe structure on a space X forces the topological complexity TC to be at least n+1, where n is the number of variables or dimensions in the problem. So for a problem like 3SAT with invariables, if it has a non-trivial Gerbe, its solution landscape isn't just rugged. It's a rugged maze with a guaranteed high level of topological complexity. This means any algorithm attempting to navigate the space needs at least n+1 distinct strategies or rules just to be able to get from any starting point to any potential solution. There's no single, simple, continuous downhill path that works universally. The landscape is fundamentally fragmented and requires complex navigation. And this is where we make the direct connection to computer science and the P vs. MP question, proving why these Gerbe-obstructed problems are computationally hard. There's a landmark theorem, or rather a set of related results building on work by researchers like Scott Aronson and Alex Arkhipov. Their work and subsequent extensions basically states that if a problem solution landscape has high topological complexity, specifically TC Gen AN plus 1, then any randomized local search algorithm requires exponential time, on average or in the worst case, to find a global minimum unless P equals NP. What do we mean by local search algorithms? This is a huge class of algorithms. It includes many common practical heuristics that computer scientists and engineers use every day to solve complex optimization problems. Things like walk-set for solving S-seat problems, simulated annealing, genetic algorithms, gradient descent, and even discretized versions of quantum adiabatic algorithms fall under this category. They typically store only limited information about the overall landscape. They don't have a global map. They move step by step from one state or configuration to a nearby one based on local information, trying to improve some score. They're essentially blindfolded explorers feeling their way around. The Aronson-Arkhipov type results demonstrate that in a landscape with high topological complexity, like the one forced by a non-trivial Gerbe, these local algorithms are fundamentally doomed. They're almost certain to wander for an exponentially long time, getting trapped in local minima or endlessly circling plateaus, unless the very foundation of complexity theory is wrong. The topological twist, the Gerbe obstruction, is not just some interesting mathematical feature. It is the direct, mathematically demonstrable cause of the problem's inherent computational hardness for a vast class of algorithms.
Okay, let's walk through that again because that's a really powerful chain of logic. This sounds like a rigorous, step-by-step proof connecting topology to computational intractability. It starts with irreversible choice, making a decision you can't undo, like setting a variable in 3SAT. That irreversible choice creates or reveals a non-trivial Gerbe, that hidden topological twist in the problem structure, preventing things from fitting together smoothly everywhere. That non-trivial Gerbe then directly forces high topological complexity, TCON+1, meaning the problem solution landscape is intrinsically a rugged, tangled maze with no simple single path to the solution. This high topological complexity, in turn, necessitates exponential search time for any local algorithm trying to find the solution, as proven by theorems related to Aronson and Arkhipav's work, unless PNP. And all of this culminates in NP hardness, the formal classification for problems believed to be intractable for classical computers to solve efficiently in the worst case. So if I'm going to understand this correctly, this isn't just a correlation. It's presented as a causal chain. A rigorous three-step proof that the perceived unsolvability or hardness of NP-complete problems is a direct consequence of the non-trivial topology of their associated Gerbe structure, which itself arises from the nature of irreversible choices within the problem.
It provides a unified framework grounded in topology and geometry that ties the abstract structure of these problems directly to their concrete computational limits. It offers a potential reason for why P is likely not equal to NP, rooted in the geometry of the solution space.
Okay, mine's slightly blown. If this twist, this Gerbe obstruction, is what makes problems hard, Can we intentionally engineer this twist? Can we use it to our advantage? Could we build things, maybe secure systems, that deliberately incorporate this topological hardness? Can we turn this fundamental difficulty into cryptographic power?
Absolutely. This leads directly to the concept of a trapdoor Gerbe as the potential basis for a completely new class of cryptographic systems. Here's the basic idea. The public key wouldn't just be a large number like in RSA. Instead, the public key itself would define the twist. It would describe a system, a space of possible messages, where the public information explicitly introduces a non-trivial Gerbe structure onto that space. When you encrypt a message using this public key, you're not just scrambling the bits according to some function. You are literally twisting the message using the Gerbes' non-trivial transition functions, embedding it into this topologically complex space, making it a jumbled mess that's incredibly hard to untangle without the right map. The beauty lies in the private key. The private key isn't just the inverse function, it's the specific mathematical object that knows precisely how to untwist the Gerbe defined by the public key. It holds the unique information needed to locally flatten the obstruction, allowing you to recover the original plaintext message. An adversary, even with the complete public key information describing the twist, cannot consistently glue the local pieces of the ciphertext back together to find the original message. They're stuck in that rugged, twisted landscape, trying to unwind a complex topological knot without knowing the sequence of moves that tied it. But you, with the private key, possess the anti-twist, the map to flatten it out, allowing you to untangle the message. Now, this approach offers a potentially stronger security profile compared to current methods. Unlike today's most common public key systems, which rely on the hardness of specific algebraic problems like factoring large integers, RSA, or computing discrete logarithms, Diffie-Hellman, ECC, Gerber-based cryptography, would rely on universal topological obstruction. It's leveraging a fundamentally different kind of mathematical hard problem, one rooted in the geometry and topology of spaces rather than number theory alone. And here's a potentially huge advantage. It seems likely to be resistant to quantum speedups. This is critical in the emerging era of quantum computing. Why? Because quantum computers running algorithms like Shor's algorithm are incredibly good at finding periodicities in algebraic structures. That's how they break RSA and discrete log systems efficiently. But Shor's algorithm and other known quantum algorithms can't factor a Gerbes cohomology class. They can't efficiently untwist a generic topological space just because it's represented on a quantum computer. The structure of the problem is different. This makes Gerbe-based cryptography a very promising candidate for post-quantum resilience, security that could potentially withstand attacks from both classical and future quantum computers.
Wow. So this isn't just a new algorithm for encryption. It's proposing a new kind of mathematical foundation based on topology instead of algebra and might naturally be immune to the quantum attacks that threaten our current systems. That sounds like a game changer for long-term digital privacy and security, like building a lock based on knot theory instead of number theory. And quantum computers just aren't designed with tools to pick that kind of knot.
It's exploring security based on topological complexity, offering a fundamentally different kind of hardness to build upon. It's still early days for practical implementations, but the theoretical foundation is compelling. And what's profound, conceptually, is that this framework reveals a deep structural duality between this idea of Gerbe-based encryption and the seemingly unrelated field of differential privacy, or DP. Think about what differential privacy does. It's a technique used by statistical agencies or tech companies to release aggregate data about large groups of people without revealing sensitive information about any single individual. How does it work? Essentially, DP aims to remove local twists and variations in the data that could betray individual contributions. It achieves this by carefully adding calibrated random noise. This noise is designed to make its cohomology class 0. It's the output space, making it statistically impossible, or at least very difficult, to tell if any single individual's data was included in the dataset or changed the final result. The goal is to hide local changes. Gerbe crypto, as we just discussed, does the exact opposite. It aims to amplify these twists to secure messages. It deliberately introduces a non-trivial cohomology class onto the space of ciphertexts, making exponentially hard unless you possess the secret key. The secret key allows you, the authorized user, to pull back that non-trivial class to 0 within your private copy of the Gerbe structure, letting you decrypt smoothly. So you see the duality. Both frameworks hinge on controlling the relationship between local details and global structure, this local to global sensitivity. But differential privacy deliberately tames it with noise to achieve privacy by flattening the space. Gerbe-based encryption, on the other hand, deliberately introduces and leverages this twist, making the space rugged and hard to navigate to achieve security. The Gerbe framework explains why this twist makes naive inversions so hard, why no amount of local smoothing or simple analysis can easily tame the complexity introduced by the non-trivial topology for these hard problems, or for secure messages in this crypto scheme.
That's brilliant. So, differential privacy tries to make the world flat, so you can't tell what changed locally, while this new crypto intentionally makes the world twisted, so you can't find your way back without the secret map. It really is like two sides of the same mathematical coin, isn't it? One used for privacy through obfuscation, the other for security through obstruction. That's a truly elegant connection, showing how fundamental this topological idea might be.
It really does highlight a deep shared principle. It's all about controlling how information propagates, how local changes affect global properties, and it shows the power of topology as a language for understanding both how to hide information and protect it.
Okay, let's circle back for a moment. You mentioned that universal West-Sumino-Witten form, theta tref chi 1 t 1 tol 3, the one that seems to quantify the universal twist. Let's look at that coefficient, that weird 1 tol pi factor sitting out front. What's going on there? Is it just a random normalization constant that makes the physics equations work out nicely? Or is there something deeper, something more profoundly meaningful encoded within that specific number?
This is where the framework ventures into some astonishing, almost philosophical territory. It suggests that this factor, $1.12, which often looks like a normalization constant needed for consistency in physics calculations, might actually encode something much deeper. We're calling it a meaning gradient. The idea is that it's not just a constant, it's revealing something about the relationship between effort, precision, trust, and meaning itself. It hints at layers of computational complexity inherent in understanding something fully. To get a feel for this, think about how we compute the value of pi. Its value comes from summing up infinite series, like some incredible formulas discovered by the Indian mathematical genius Ramanujan. For example, one of his formulas looks like this: 1103 plus 263947 is 4k. Computing just the first term, k0, gives you a rough estimate of pi. Computing the second term, k1, adds about 8 more digits of the third term adds another 8, and so on. So computing pi to higher precision mirrors the process of uncovering deeper meaning or gaining a more refined understanding. Each successive layer of precision yields a more accurate value. Here's the crucial part. Look at that $4 term in the numerator. That factorial grows incredibly fast. This means that calculating each subsequent term, each additional layer of precision, requires exponentially more computational effort. This creates a kind of computational stratification. Each layer of deeper understanding, each jump in precision, demands a significantly higher computational cost. This structure naturally builds what we're calling a gradient of trust, or a meaning gradient. A shallow understanding, represented by computing only a few terms, comes with a low computational cost, but also inherently lower confidence in its completeness. Conversely, achieving a deep understanding, which requires computing many terms of the series, demands a very high computational cost, but it also results in high confidence in the precision and reliability of that understanding. Perfect understanding, analogous to computing an infinite number of terms, becomes an impossible asymptote. You can always go deeper, always refine further, just as true meaning often seems to have infinite depth. That wide error 12 pi factor appearing in the universal twist formula might be a fundamental mathematical reflection of this principle, how effort, information, and computation are intrinsically linked to the gradients of meaning and trust. It suggests the universe quantifies the cost of deep knowing.
Okay, so the more effort, the more computational work you put into really understanding something, into digging into its complexities layer by layer, the more meaning you extract from it, and the more you trust that understanding because you've done the work. You're saying this isn't just a psychological observation. It might be literally built into the mathematical constant that defines the fundamental twist in these hard problems. That's truly mind-blowing. Like the universe itself has this built-in accounting system telling us that true, deep understanding comes at a cost. And that cost grows exponentially the deeper you go.
It suggests that the universe has a meaning gradient woven into its fundamental mathematical structures. The act of knowing, computing, or solving hard problems is about navigating that gradient, investing increasing effort for increasing clarity and confidence. It's quite a perspective shift.
Let's talk about a concept we usually think of as profoundly simple. The number 0. We typically think of 0 as just nothing, right? The absence of quantity, an empty set. Is it just an absence in this framework you've been describing? Or does this topological Gerbe-based perspective redefine 0 in some radical way?
In this framework, 0 gets a radical redefinition. It's proposed that zero isn't merely nothing, but represents the epistemic event horizon. It's the ultimate boundary of what can be known, computed, or resolved. It's a fundamentally opaque point beyond which information becomes inaccessible or distinctions collapse. In computational terms, zero might correspond to where computation becomes undecidable, like the halting problem. It's the point of zero resolution, where you can no longer distinguish between different states or outcomes reliably. In topological terms, zero can be where coordinate systems break down, where manifolds might have singularities, points where the smooth structure unravels and our usual descriptions fail. In information theory, zero information corresponds to maximum uncertainty or maximum entropy. It's where our ability to predict or know anything vanishes. Now, connect this back to the Gerbe and its twist, quantified by the WZW form. In Gerbe terms, when the WZW twist approaches zero, it doesn't necessarily mean no twist in the sense of the space becoming perfectly flat and simple. Instead, it could mean that the twist has become unknowable or unresolvable from our perspective. The Gerbe hasn't necessarily disappeared. It might have, in a sense, collapsed into a singularity of unknowing, a point of fundamental, unrecoverable information loss or ambiguity. This perspective connects zero to the idea of ultimate irreversibility, perhaps representing a choice or an event that, when it occurs, fundamentally erases its own history or makes its prior state completely inaccessible to any future observation or computation. Zero, in this radical view, becomes the convergence point of all unsolvable questions, the singularity from which meaning or information cannot escape. And germs, with their twists and obstructions originating from irreversible choices, become the algebra of irreversible knowledge. They provide the mathematical language to model how information can become irretrievably lost, or how problems can become fundamentally topologically difficult to access or solve.
Wow, this has been an absolutely incredible deep dive. We've journeyed from that familiar, frustrating feeling of hitting a wall with an unsolvable puzzle into the very fabric of meaning, the limits of knowledge, and even a redefinition of zero. Let's try to bring it all together for our listener one last time. Let's walk them back through the entire journey, the unified thread we followed in this deep dive. We started with that simple, very relatable idea of irreversible choice, just the act of making a decision you can't perfectly undo, like flipping that coin in the puzzle or making a measurement. We saw how this action mathematically creates or reveals a Gerbe twist in the fundamental structure, the possibility space of a problem. It prevents things from gluing together smoothly and consistently everywhere, especially when three or more paths or patches interact. This topological twist, quantified by the non-zero DD class, in turn, directly leads to computational hardness. It explains why problems like 3SAT and potentially PVZNP are so intractable for our standard local search algorithms. Their solution landscapes are fundamentally rugged and maze-like due to this twist. And finally, we discovered how this very same mechanism of topological hardness, this engineered twist, holds the secret to a new kind of cryptographic power. It allows us to potentially engineer intrinsically secure communication systems that might even be resistant to attacks from future quantum computers.
And what's truly revolutionary about this perspective is the emergence of what you might call a universal law of difficulty. Hardness, in this view, isn't just some random ad hoc barrier that's unique to each difficult problem. It's not just a matter of things getting too big and complex through combinatorial explosion, although that happens too. Instead, at a deeper level, it's proposed to be a measurable geometric feature specifically, the Dixmer-Doherty class of an underlying gerbe. It's a form of intrinsic curvature or torsion in the problem structure itself, a topological invariant that often can't be smoothed away or easily overcome. This even suggests profound philosophical implications, that the universe might have this meaning gradient built into its most fundamental mathematical structures, and the very act of knowing, of computing, of solving problems is fundamentally about navigating that gradient, paying an increasing cost for deeper understanding.
This framework, this way of thinking, it seems like it could open up entirely new avenues for exploration, right? New ways of approaching challenges in science, math, computation, maybe even other fields. Challenges that have seemed insurmountable for decades. It really could change how we think about what's possible to solve or understand.
Indeed. The grand challenge now for mathematicians, physicists, computer scientists is to develop the new mathematical tools needed to navigate and work within these topologically twisted spaces effectively. This framework compels us to build bridges between fields that were often considered separate. Deep number theory, abstract geometry and topology, quantum physics, and theoretical computer science. It holds the promise of leading towards a more unified theory of obstruction, a common language instead of tools to understand why certain questions across all these domains resist our current methods, and maybe revealing pathways to untwist or circumvent these obstructions in certain special cases. It's the frontier.
And as we sign off today, here's one last provocative thought. If irreversible choice creates these Gerbe twists in computation, fundamentally altering the landscape of problem solving, what about the choices made in our own minds? Could these same mathematical structures, these Gerbe twists, be the mechanisms of conscious decision-making? Could they explain why some choices feel so final, shaping the landscape of our future possibilities? Join us next time on The Deep Dive as we explore that very question. How might Gerbe twists underlie conscious decision-making? Thank you for joining us for another mind-expanding deep dive.